Hello everyone. Welcome to Lab 9, Part 1. It will take more time to explain and demonstrate this lab, so we will separate this into two parts. In Part 1 of this lab, we will be introducing the topic of motor positioning, how the MOVIDRIVE uses a scaled value to travel to a target position using measurement units, and we'll demonstrate the different reference routines that the MOVIDRIVE can perform to find the starting point of an application. At the end of Part 1, you will have a better understanding of the details that are a crucial part of how the MOVIDRIVE can perform positioning movements. In Part 2 of this lab, we will step through configuring an application module that downloads a positioning program to the MOVIDRIVE. We will then demonstrate operating the MOVIDRIVE with the program we downloaded. A common positioning application will convert the rotational movement of a motor into linear movement of equipment the motor drives. The MOVIDRIVE will use a scaled value to determine the number of motor rotations required to reach a specific distance. The first part of determining this is calculating the amount of encoder pulses that will happen as the motor rotates. You can connect numerous types of encoders to the MOVIDRIVE, and they can be different resolutions. Having different resolutions, though, could make it more challenging to fine-tune and troubleshoot the positioning accuracy. So the MOVIDRIVE will always equate one rotation of the motor encoder as 4,096 pulses. Even if we were using a common encoder resolution of 1,024 pulses, the MOVIDRIVE will automatically upscale that to equal 4,096 pulses per rotation to make the scaling consistent. So when we look at this encoder pulses equation, this 4,096 increment value will be a constant. A lot of times the motor is attached to a gear reducer, and that ratio has to be multiplied in. And if there is additional ratio from sprockets or more gearboxes, we have to account for that as well in this equation. If we multiply all those values together, it represents how many encoder pulses will occur if there is one full rotation at the driving wheel or the final gearbox output shaft. Now that we know the total number of encoder counts to make a full rotation, we can introduce a new equation to represent a scaled position. So next, we need to determine the distance that is traveled if there is one full rotation at the driving wheel or the final gearbox. It will depend on the application, but there are numerous options for the type of measurement unit that we could use. I will mention that the scaling should be as precise as possible, otherwise it could cause issues. So we commonly use units like degrees, millimeters, tenths of a millimeter, or inches. I don't recommend using units like feet, yards, or meters in the denominator of this scaling equation for the distance because of the reduced precision. There are a couple methods to determine the distance that the equipment will travel as the motor rotates. We can use equations to determine this distance, or we can manually move the equipment if it is safe to do so and determine it with physical measurements. For example, if the equipment is too complex to determine all of the gear ratios and wheel or pulley diameters, we could use a manual move between point A and point B of the application to determine the numerator and denominator for this position scaling equation. We would first record the starting encoder pulses that are shown in the MOVIDRIVE at point A. Then we can manually move the equipment to point B and record the ending encoder pulses that are shown in the MOVIDRIVE. The difference in encoder pulses from point A to point B would be the value that we would use in the numerator of this equation. Then we can use a tape measure to determine how far the equipment traveled between point A and point B, and that value will be placed in the denominator as the distance. To further help visualize why this position scaling equation is necessary, let's look at this demo motor that has a flywheel and no gearbox or additional ratio that we have to account for. Since there are no additional ratios, we know that the MOVIDRIVE will report 4,096 encoder pulses for one rotation of the flywheel. Now we need to determine the linear distance the flywheel travels in one rotation. The diameter of the flywheel is 150 millimeters, so we can just calculate the circumference to determine the distance traveled for one rotation. The circumference equation is pi times the diameter, and if we plug in 150 millimeters, the circumference will result in 471 millimeters of linear travel for one rotation. Now we can plug in the values into the numerator and denominator of this position scaling equation and find that the scaling factor will be 8.7 encoder increments or encoder pulses for every millimeter of linear travel. Now when we send a positioning command to the MOVIDRIVE, we can use a linear distance as the set point instead of having to use the total amount of encoder pulses as the set point. So still using this demo motor with a flywheel as an example, if we needed to travel to a set point of 1,000 millimeters, the motor will have to rotate the encoder 8,700 increments to travel that distance, which is slightly more than 2 full rotations of the flywheel. If you're using an application module to create a positioning program on the MOVIDRIVE, it can calculate this position scaling for you if you know all the gear ratios and diameters. If you don't know those values to get the application module to calculate it, then that's okay too, because you can still manually enter the numerator and denominator from the position scaling equation. Whether you calculate the scaling manually or have the application module calculate it, you should always fully test the application and conduct scope recordings if needed to verify it is operating properly. If the position scaling is incorrect, there are some common signs that would indicate that. The motor could rotate at an incorrect speed, or it will stop in a position that is different than the intended travel distance. Also, the MOVIDRIVE could issue an F42 fault, which is a lag error, meaning that the MOVIDRIVE can't maintain the speed and acceleration needed to travel to the set point position. Now that we know the MOVIDRIVE will scale different encoder resolutions to a constant of 4,096 pulses per rotation, there are other factors about encoders that can change how the equipment is operated. A common type of incremental encoder uses disks to count the pulses as it rotates. There is no memory storage in these types of encoders, so if there is a power loss or a reset on the MOVIDRIVE, the position will be lost. The different disks are called the A track and B track, and they will be offset from each other to create the A and B channels of the encoder. There is also the possibility of a zero pulse mark that happens once every rotation of the encoder. Not all encoders are made with the zero pulse mark, but it can be used for certain referencing or alignment routines if the encoder does have it. If you aren't using an incremental encoder, then the common other type of encoder that can be used is an absolute encoder. There are two categories of absolute encoders called single-turn and multi-turn. The single-turn version only has enough position tracks to count one full rotation of the shaft. If the encoder turns past one full rotation, the counts will start back over at 0 and count until the next full rotation. A multi-turn is similar in that it counts the position points in one full rotation, but it also keeps track of how many rotations the encoder has made. So the multi-turn encoder doesn't have its position start over every rotation. It could take thousands of rotations in a single direction before it runs out of counts and has to start over again at 0. An example of an absolute encoder disk is shown here. The pattern in the center are the absolute position tracks, and each one is unique to a specific shaft angle. So even if the encoder loses power, once power is back on, the unique shaft angle can be determined from the pattern. Because of this design, applications that use this type of encoder don't require frequent re-referencing routines. Absolute encoders can also have an incremental track and a zero pulse mark to make them more compatible for different applications. The reason we're talking about the different types of encoders an application can have is because it will affect the overall operation and how the reference routine should be handled. If you're unfamiliar with what referencing means, this is a process a positioning application uses to move the equipment to a known location before the application starts operating. This is also commonly called a homing routine or setting the encoder pulses to 0. During commissioning, we have to configure which reference routine the MOVIDRIVE should perform to put the equipment back into a starting position or a machine 0 position. During normal operation, the reference routine is usually the first thing that has to be performed before the equipment is allowed to position. Like I mentioned previously, this will be very common for applications that use incremental encoders, since their position can be lost from a power cycle or a fault reset on the MOVIDRIVE. However, if the application uses absolute encoders, those may not require re-referencing since the position is maintained after a fault reset or a power cycle. Some exceptions to that are when the motor or encoder is removed or replaced for maintenance, or if the machine 0 position needs to change to a different location. In those situations, the equipment would need to be re-referenced since there were mechanical changes that altered the encoder position. There are many different ways for the MOVIDRIVE to operate a referencing routine, and in the parameters, these are called referencing types. The MOVIDRIVE has 9 of these types, and each one is a different method to put the equipment into a machine 0 position. A lot of factors have to be considered to choose one of the 9 referencing types the application should use. One of the biggest factors is what type of sensors are installed that can be used to determine the starting position. So let's demonstrate some common ones that could be used. A lot of applications use limit switches. These mark the ends of the permitted travel range for the application. If the equipment contacts either sensor, it should be configured to stop it immediately to prevent it from crashing. The sensors are typically normally closed, so the circuit won't open until something is contacting the switch. The MOVIDRIVE can use these to determine the end of travel in one direction and the start of travel in the other. Here's an example of what happens to the state of the limit switch if it is contacted. The equipment traveled to the left limit switch and the sensor signal was high. It contacted the switch, causing the sensor to go low, and now it's stopped on the switch until it's backed off. So we can back the equipment off of the switch and it will go high again. And if the equipment travels to the right switch, it will make the signal go low, then it will be stopped on the switch until it's backed off. Once it's moved off the right limit switch, it will go high again. Another type of signal we can use for referencing is the 0 pulse of the encoder if it has one. Depending on where the encoder shaft is currently at when the referencing routine is started, it may have to make a full rotation to reach the 0 pulse. If the motor is connected to a gear ratio, you may not be able to physically see the equipment aligning to the 0 pulse of the encoder. Also, the 0 pulse signal is commonly used along with other sensors such as limit switches. Here's what it will look like as the equipment moves until the 0 pulse is found. Another type of sensor that is common are reference cams. These are sensors that can be placed at any part of the application inside of the limit switches. It is a dedicated switch specifically to mark the home location or the machine 0 position of the equipment. These sensors are different from limit switches. These are normally open and are not used to immediately trigger a stop on the equipment if it's contacted. The reference cam can be used by itself or along with other signals such as limit switches or a 0 pulse from the encoder. For this example, we'll demonstrate it with just the cam sensor. The equipment travels and then it will contact the cam sensor. making the signal go high. It then automatically reverses direction and backs off of the cam sensor until the signal goes back low. If we combine a 0 pulse signal with the cam sensor, this is what it would operate like. The equipment travels to the cam, then it backs off of the cam, and then it keeps moving the additional amount needed to reach the 0 pulse of the encoder. Another point of referencing is the speed that the equipment travels at when it's performing a referencing routine. There will be two motor speeds that are possible. The fast speed number 1 has a default setting of 200 RPM, and the slower speed number 2 has a default setting of 50 RPM. These can be changed in the MOVIDRIVE parameters for different needs, but it's recommended to use slow speeds for both and make sure that speed number 2 is slower than speed number 1, because the referencing routine will automatically switch from speed 1 to speed 2 at specific phases of the move. If these speeds were set too fast, it could present unnecessary risks when the equipment is attempting to locate the machine 0 position. Like I mentioned previously, there are 9 referencing types to choose from. With the sensor options we just went over, we can divide this into 5 categories depending on what type of sensor is being used and the type of movement the equipment will make to find the machine 0 position. The reason we should understand these types is because the application module will have a numerical selection that represents one of these 9 types. So we will summarize how each type works so we can visualize how each routine will differ. We're going to start with type 0 and work our way to type 8 as we demonstrate these. Type 0 will have the equipment run in the counterclockwise direction at the slower speed number 2 until the encoder 0 pulse is found. Then the equipment will be referenced at that location. One reason why there are numerous types to choose from is because 2 types will have a similar function, and the only difference will be the direction the referencing routine travels, either to the left or to the right. So I will combine some of these types and only demonstrate one direction, so explaining these doesn't get repetitive. Type 1 and Type 2 will combine the reference cam switch along with limit switches that we demonstrated earlier. The equipment will travel to the left or the right to find the reference cam and stop close to it and be referenced at that location of the cam. You could place this switch anywhere inside the limit switches to be where you want the equipment to set the machine 0 position. We're going to use Type 1 as our example, and the equipment is currently on the right side of the cam switch. So let's look at how it handles the reference routine in this scenario. We will see the equipment run at the faster speed until it contacts the cam. While it's on the cam, it uses the slower speed number 2 and travels to the left side of it. Then the MOVIDRIVE will say it's referenced after the equipment is clear from the cam on the left side. Here's another scenario of Type 1 or Type 2, and a reason why the limit switches are used along with a reference cam switch for these 2 types. Let's use Type 1 again as an example, but this time the equipment will be located already on the left side of the cam. If the equipment is already to the left, then it will continue traveling left at speed 1 until it contacts the left limit switch. At that point, it will automatically back off of the limit switch using speed 1 and travel until it locates the cam. Then it will slow to speed 2 and back off of the cam until it's clear, and then set the reference at that position. The next types we'll demonstrate are 3 or 4. These don't use the reference cam switch and only use the left or right limit switch as a machine 0 position. For this example, we'll use Type 3, where the equipment is going to travel to the right limit switch to find its 0 position. It will start with speed 1, and once it contacts the limit switch, it switches to speed 2 and backs off of the switch. Then it sets the reference at that position. Type 6 or 7 will bring back the reference cam, but in this scenario, it has to be flush or just slightly in front of the limit switch. If the limit switch signal changes before the cam does, then it will issue a fault. So the cam has to be positioned correctly for these types to work. We're going to demonstrate type 7, where it's going to reference using a cam on the left limit switch. It's going to move at speed 1, then contact the cam along with the limit switch and back off of both. Once it's clear of both switches, it will set the reference in that position. The last two reference types we will demonstrate don't physically travel when the reference routine is started. Since these don't have a physical move that happens, we would have to manually move the equipment to the location where we want it to set the machine 0 position. So we would jog the equipment or put it in manual mode to move it where it needs to be. Type 5 requires the MOVIDRIVE to be enabled. Then we will start the reference routine with the MOVIDRIVE enabled. And since there is no further movement, it is referenced right where it currently is positioned. Type 8 will be very similar to Type 5, with the exception that the MOVIDRIVE does not have to be enabled. So we will manually move the equipment to where we want it to be referenced at. Then start the reference routine, and since it doesn't have to be enabled, the reference will be set where the equipment is positioned. Since the MOVIDRIVE doesn't have to be enabled for this reference type, it's possible to set the machine 0 position even if the MOVIDRIVE is only powered by 24 volts and doesn't have line voltage. These reference types that don't have any movement when they're started are common with applications that use absolute encoders, since those don't require regular referencing routines. In those situations, it's likely not an issue to have to manually move the equipment to where the machine 0 position should be, since it's very infrequent to have to do that. All right, this concludes part 1 of Lab 9. In part 2 of this lab, we will go into the Motion Studio software and go through the steps to commission an application module. We will download that to the MOVIDRIVE and then reference the machine 0 position. Then we will operate the positioning application from the digital inputs of the MOVIDRIVE. Thank you for your attention. Take care and have a good day.